Hello and welcome to another video in the Reigate Maths series for the second year integration. What this video is going to cover is integration using trig identities. So when we talk about trig identities, it's all of the identities that you've learnt about in the first or the second year. So things like sine squared plus cos squared, which equals 1. Sine over cos, tan x, but could also include ones that you've learned in the second year. So things like cos x over sine x, 1 plus tan squared is sec squared, or 1 plus cot squared is cosec squared. Could also use double angle formulae. So for sine 2x, cos 2x, and any of those. Or tan 2x. This one is far less common because there's lots to it. So you need to be able to not only use these and integrate with them, but also just recognize when they're appropriate, which is quite difficult to do because there's a lot there. But it only really comes from experience and thinking about, well, I can't integrate this function. Is there some trig identity that links to a function I can integrate? So take our first example. Integrating tan squared x. So tan squared is not something we can integrate. Tan x we can in a very roundabout way, or we can look in the formula book to get an answer for tan x. But tan squared, not so much. So we need to think, okay, how can I relate tan squared x to something that I can integrate? So let's look at our trig identities. First off, let's have a look at which ones involve tan. So we've got this one, we got this one, and we got this one. This one's irrelevant because, yes, it's got a tan squared in, but there's lots of other nonsense there as well. So really, we're only looking at this one or this one. So if we think about sine squared over cos squared is tan, is that going to help? Well, if we substitute it in, we're going to get sine squared x over cos squared x. That's not a thing we can integrate, so that one doesn't help. So we're now just down to this one, and oh look, it's got sec squared x in it. If you cast your mind back to the previous video on trig integration, we said that sec squared x, that's a thing we can integrate. So we need to rearrange this. So we know that 1 plus tan squared x is sec squared x. So tan squared x is sec squared x minus 1. Sec squared x we can now integrate. That's in the formula book. It's tan x. 1, well, that integrates to x, and we get our plus c. So not a lot of working, but it's this first step. If you can't recognize this step, you cannot do the question. So you need to become very, very familiar with these and be able to use these almost with your eyes closed. So let's have a think about cos squared x. So we're going to look at one way to do this question now, but there is a second way to think about it. later on, potentially. We may get to that in a later video, we might not. This is the easiest way to think about it though. So, cos squared x. So let's go back to our identities and let's have a look at which ones have cos squared in. There's not many. It's this one and this one. So let's have a think about this one. So cos squared is 1 minus sine squared. If we use that in here, is that going to help? Well, no, because we get the same problem that we're finding with the question itself. We can't integrate sine squared x. So we have to use this one here. So we know that cos 2x is equal to 2 cos squared x minus 1. Remember, these double angle formulae you need to learn. Yes, you can derive them using formulae given in the formula book, but for questions like this, you need to be able to use them quickly. You don't have time to derive them. So let's look at how we rearrange this one here. So we can rearrange to make cos squared x the subject. So we get 2 cos squared x is cos 2x plus 1. So cos squared x is a half cos 2x plus 1, which means that the integral we're trying to find is the integral of this. Now, because the half is there, I'm going to stick the half on the front. You don't need to, but you can do. So cos 2x, integrating cos 2x. So cos integrates to sine. The 2x stays there, and we divide by the coefficient of x. And then 1 integrates to x. So this is a quarter sine 2x plus a half x plus c. If you're required to integrate sine squared x, it works in exactly the same way, which is what our next example is going to do. So here we go. Find the exact value of the integral of sine squared x evaluated between pi over 12 and pi over 8. So don't forget, exact value is important. That means that our answer is going to have pi's in, or surds in, maybe a bit of both. But on the whole, this problem works exactly the same way as the previous one. We know that 1 minus 2 sine squared x is cos 2x. So sine squared x is a half 1 minus cos 2x. Therefore, the integral between pi over 12 and pi over 8 of sine squared x is the same as half of the integral using the same limit (1 minus cos 2x). Now we integrate as we've always done. 1 integrates to x, cos 2x, half sine 2x, as we've seen, and we evaluate that between pi over 8 and pi over 12. Now this is where things get a little messy, but there's lots going on. So we've got a half, big bracket, pi over 8 minus a half sine 2 pi over 8, so pi over 4, minus bracket pi over 12 minus a half sine pi over 6. And close all our brackets. Now be careful with this. With this example, it's probably not too bad. If we just stick all that in our calculator, it may well give it to us exact, but it might not. So if you can't do this whole thing in your head, which is fine, do each bit separately. So work out a half sine pi over 4. Work out a half sine pi over 6. And then do it in bits. Don't try and stick this whole thing in your calculator, because you may just get a decimal, which we're told we want the exact value. Writing down all of the numbers in your calculator is not exact. So let's do this in bits. So we've got a half. So now we've got pi over 8 minus pi over 12. So using our calculator, pi over 8 minus pi over 12. So we're told, our calculator tells us it's pi over 24. Let's do the other bits. A half sine, check I'm in radians mode, which I'm not. A half sine pi over 4. So I get root 2 over 4. So this is minus root 2 over 4. I've already dealt with the pi over 12. So minus minus plus a half sine pi over 6, which is a quarter. So we can now see, tidying it up-ish, that we're going to get 1 minus root 2 over 8 plus pi over 48. Which is not particularly nice, but it's exact. Because this is not a particularly nice answer, you might want to check it on your calculator. So if we go to our calculators, making sure you're in radians mode, let's type this in. So we go to integral. Now, your calculator can't cope with writing sine squared, so we've got to do things in a little bit of a roundabout way. So we're going to go brackets, sine x, close brackets for the x, and then close brackets for the sine, and then square that. Our limits are pi over 12 and pi over 8. Oops. And we press equals. And we get a decimal. Well, that's not that. Or is it? Well, we don't know. So what we can do is we can now type in our answer. So fraction 1 minus root 2 over 8 plus pi over 48. And we can see we get the same decimal. Now, obviously, it could be that down here, off the screen, we've got slightly different decimal places, but it's unlikely. Because we've got 2, 4, 6, 8, 10, 11 decimal places correct, chances are we're right. So this is a really useful way to check whether your exact answer is correct. So this next example is a little bit trickier because it's not obvious necessarily which trig identity we're going to use. There's no squareds, there's no tans, there's no cot, there's no cosec. So typically thinking about the trig identities, you can't come up with one in your head. However, we need to think about the double angle formulae. Let's ignore what's inside the trig for the moment and let's think, what do we have that has a sine times a cos? Well, we know that sine of 2a is 2 sine a cos a. Well, this bit here is very similar to what we've got here. So let's think about how we can link these together. We've got sine a cos a, and we've got sine 3x cos 3x. So let's think about sine 3x cos 3x. I know there's a 2 on the front, but that's because there's a 2 here. We'll come back to that later. How can we use this double angle formula? Well, it's sine of 2 lots of whatever this angle is. So 6x. Now we're not trying to integrate 2 sine 3x cos 3x. We don't want the 2. So how do we deal with it? We get that this is equal to a half sine 6x. Then following our normal rules of integration, sine integrates to minus cos. The 6 deals with it this way and becomes a 6th. So we get minus 1 over 12 cos 6x plus c. So this is what I was saying earlier about really having to be able to notice bits of your trig identities. In this case, you had to notice a part of a double angle formula. Now the next example we're going to look at is slightly cheeky, in so much as it's not on one of the lists that I wrote out before, but it's something that in theory could come up. And it's this one. Now there are a few ways you can do this question. First time I did this one, I went about a very long method of splitting this up into lots of sine x and cos x's, and then integrating each of those separately. I got the right answer, but in a very roundabout way. The thing with this one is there's actually a rule in the formula book that's linked to the addition formula. So if we look here, we can see we've got the addition formula here. We've got these extra ones underneath. So this is how we can think about, well, what happens if our angles are different. So we have still a sine times a cos. So let's look at these here. Now we've got two options for sine times a cos, or cos times a sine. So we've got these two options. I'm going to use this top one because, well, I don't want to have to deal with the fact that it's a minus here. So I'm going to use the identity that sine A plus sine B is 2 sine A plus B over 2 cos A minus B over 2. So this is the rule that's in the formula book that I'm going to use. Now all we need to do is figure out what A and B are. Well, we know that A plus B over 2 is 3x, and A minus B over 2 is 4x. Sorry, 2x. So A plus B is 6x, A minus B is 2x. We just solved these simultaneously. So this tells us we add these two equations together, we get 2a equals 8x, so a is 4x, which means that b is 2x. So therefore, the integral of sine 3x cos 2x is equal to, now it's a half because we've got a 2 here, sine of A plus sine of B. And now we just integrate each of these as we would normally. So we've got a half, sine goes to minus cos, so this is minus a quarter cos 4x minus a half cos 2x plus c. Yes, we could then expand this to give us a somewhat nicer answer. Minus 1 over 8 cos 4x minus 1 over 4 cos 2x plus c. Not very nice, but very useful properties to think about. Now, chances are, something like this, if they bring it up in the exam, might be not particularly nice of them, but it's something that they could do. So it's really something to be aware of. But on the whole, the questions are going to be things like this, where you have to notice parts of trig identities or the double angle formula. Thanks for watching.